In acoustics, especially which are used in MEMS, there are a certain category of modes within the bulk modes which exhibit extremely high quality factor. So for here, we'll look into two examples, that is the lame mode and the wine glass mode. Lame mode and wine glass mode are extensively explored in the capacitive transduction scheme. Let us have a look at what is lame mode. So Lame mode here, for example, has been taken from Professor Ashwin Sheshia's group in Cambridge, where they use a square plate resonator made up of a single crystalline silicon to excite it into Lame mode. So this is the vibration pattern of the Lame mode with a quality factor of reaching 1.16 million. Similarly, this is a work from Professor Nguyen's group in UC Berkeley, where they have used a circular resonator structure to realize a wine glass mode. This is the deformation pattern for wine glass. And here also, the central structure, that is a resonator element, is made up of a single material. Here is polysilicon. So when we look into these two examples, one very striking commonality is that the central resonant tank, that is the main vibrating body, is made up of a single material, and in most cases it's a high Q material, and they do not suffer from interfacial loss as there is no material stacking. And as you can see over here, this anchoring is very ideal. That is, they are anchored at the nodal point. That means the anchor loss is also minimal. From the previous slides, we have understood the importance of a high Q performance. And in all these previous slides, we have seen quality factors going up to say just 20,000. But there are modes which does have quality factors in the range of millions, but it is not possible to harness these modes using the conventional transduction scheme. Now, what is the reason behind it? The reason, like we already know, that piezo MEMS depends on the conversion of electrical to mechanical domain. And while under vibration, as particular strain profile is generated for a particular mode of interest, now, this is the strain profile for the Lame mode of vibration. As you can see over here, that the tensile and the compressive regions are quite close to one another, which means that if we are to place an electrode over here, we will be resulting in net charge cancellation because of the very close proximity of opposite polarity strains, which leads to charge cancellation. And when there is a charge cancellation occurring, it is difficult to realize using piezoelectric transduction. So even if the mechanical motion can be induced, it will be very weak. And at the same time, the charge is being cancelled, and hence the motional resistance will be higher. The works were done to use this particular Lame mode. As you can see over here, there is a four-port measurement scheme as anticipated. Even though the quality factor we can reach about 25,000, due to the poor transduction ability, the motional resistance is in the range of 750 kilo ohm. So there were works starting from 1995 to recent years where there were many efforts done to excite this particular Lame mode, which actually has extremely high quality factor, but due to the reasons mentioned in the previous slides, it was not possible to efficiently excite these modes. What is generally done, we'll take an example of a wine glass mod. So what happens in conventional piezo scheme is that we put the electrodes over the high Q bulk mode itself. So the drive and the sense occurs on the main resonant body. So as this is a two-port scheme, this is a four-port scheme, and this is the SCM image of this particular device configuration. Now, it is quite obvious that there is material stacking, and hence there will be interfacial loss as well. And since driving and sensing happens on the bulk mode itself, they have to be patterned to meet the strain profile. And also for these kind of modes, for Lame mode, it's easier to find an anchoring point, but certain bulk modes do not have an ideal anchor point, and hence the anchor loss is higher. So here we can see that patterning electrode in the bulk for wine glass is relatively easier, but the Lame mode that we saw earlier, it is very intricate design, and hence it becomes close to impossible using the traditional fabrication schemes. So this is the bottleneck that is being faced by the researchers till late. So what we did in our work is that we came up with a new topology known as the support drive sense concept. What is the difference here is that earlier we would place the transduction on the high Q block, right? But here what we do is that we remove it away from the high Q mode and use an alternate mode to drive this particular high Q resonant tank into resonance. And hence, since there can be multiple supports, we can have multiple drive sense configuration. And we already know that for this particular wine glass where two of the arms are always out of phase, we can use differential operation to reduce the feed through and also eliminate the spurious mode. So the measurement results I'll show in the upcoming slides. This is an SEM of the wine glass mod resonator. Here we zoom in into the transducer layer, that is a thin film piezoelectric material. We use aluminum nitride. Top electrode is formed by 1 micrometer thick top aluminum, and then the bottom electrode and the device layer both are of 10 micrometer thick silicon. So this idea had to be validated using FEM analysis. So this is the Lame mode resonator displacement profile. As we know that the corner points are close to ideal anchor points because they do not feature much but displacement. Okay. But then this is the strain profile, which means that the net strain, if you are to calculate, then it results to zero. When the net strain is zero, that means the net charge generated during this motion is also zero. Here, what we do is that we use a length extension mode resonator. As the name itself indicates, the motion is along the length axis. So this particular resonator is of interest because it does have a good anchoring point, and also at a given point of time, the length extension mode is either undergoing compression or tensile. Both is not happening at the same time. And that means that we have a high strain region, and this particular region can be used for electrical transduction. That means we can place our electrode, the drive and the sense electrodes, on the length extension mode resonator. Hence, we design the resonator such that both of them have the same resonant frequency, and we acoustically pump the energy from the LE mode to the Lame to actuate this bulk mode. So what happens is that when we combine them, we get this particular arrangement using mechanical coupling. And as you can see here, the positive and the negative strains are very far from one another. That means there is no way that the charges will get cancelled. This is a measurement result of a wine glass mode resonator. As you can see, we have gotten a quality factor close to 8,000 with a very low motional resistance of 1,800. The device is being placed in vacuum in a prop station. This is a PCV level measurement. This is in vacuum lecture prop station. We vary the power, and also we see that we get very good linearity. The quality factor is enhanced. We reached about the loaded quality factor is about 9,900. The unloaded quality factor is slightly about 10,500. And this is the different measurement schemes. One is the 2-port measurement scheme. The other is the 4-port measurement scheme. We can see that, as I mentioned earlier, for this particular radial contour mode, what happens is that all these particular transducers are undergoing same strain profile. So when we do a differential measurement, the mode gets cancelled off. But when we do a 2-port measurement, because there's no cancellation of this particular strain, because we are just using 2 arms of the resonator, we can see both of these modes. Hence, we can use differential scheme to eliminate the unwanted mode and just to have the mode of interest. Once this particular idea or the prototype was being validated, we moved on to the next stages as to how can we improve the device performance. So this is the material engineering aspect. So as we know, MEMS cap provides 1 micrometer aluminum, 500 nanometer of aluminum nitride, and 10 micrometer of silicon. So this is the transducer thickness distribution that was profiled using Keyence. And we can see that, this is the aluminum nitride, which is around 500 nanometer. Then we have close to 1 micrometer thick aluminum top electrode. And we all know that thicker the metal, lower the quality factor. So we had a chance to have a run where we had 500 nanometer gold. So what the only difference is that here we have a 1 micrometer thick aluminum, and in here we have a 500 nanometer thick gold. So these are the different performances of the devices. Please note that the stop and rejections are different because the measurement conditions were different. And this is the performance matrix. We can see that with a 1 micrometer thick gold, the quality factor is close to 10,000. But when you reduce the thickness of the metal, it goes down to 13,000. And when there is an increase in the quality factor, a proportional decrease in the motional resistance can also be observed. The next one is the structural engineering. So far we have seen a full coverage area. Now we remove the full coverage support and replace it with notch support. So this is the traditional and this is the improvised design. And as you see that we tried out in simulation and the transduction was quite successful, it is still able to excite the wine glass mode of resonance. And let us look into the performance of the device as anticipated, because the stiffness of the device is being modulated. When you change the transducer area, we'll definitely see some changes in linearity, but that can be a different topic. Here we will focus mainly on the quality factor enhancement. So here we see that the quality factor jumps from 13,000 to 15,000. So this is yet another way of using structural engineering to boost the quality factor. So the first generation designs were a Q of 8,000, and now we are able to attain quality factors of 15,000. So these are all without any anchor optimization. So there is a large area that we can study by optimizing the anchors. For example, phononic crystals, reflectors, notches, dispersion engineering, etc. That was all studied in the previous section, can be applied here to improve the device performance. So next we shall move over to the another aspect that was studied using support transducer is that so far we had multiple transducers to excite a single bulk mode, right? Now let us look how one transducer set can excite an array of high Q resonant tanks. So higher the volume of high Q resonant tanks in a resonator system, we anticipate a higher quality factor. We did finite element analysis to see if it was feasible. And as you can see, the width extension mode resonator can successfully excite an array of 2x3 Lamé mode resonators on each side of the transducer. So generally what we see in the previous cases is that we use the dead band of the phononic crystal, right? Here, instead of using the dead band, we are using the resonance. Why? Because phononic crystals are made up of single crystal materials. So why not use the high Q feature of this single crystal material and operate them at one of the high Q bulk modes that we know, which is the Lamé mode, to get an extremely high performance. So as you can see over here, this is the fabricated device. The device was measured in both air and vacuum to see the effect of squeeze film damping. So this is one of the highest quality factors that we have attained, and the unloaded quality factor actually goes above, so this is the unloaded quality factor. So this is about 58,000, and the motional resistance is about 1.25 kilo ohms. So as you can see that there is a huge enhancement in the performance by just pumping down the ambient pressure. That means a vacuum, this particular Lamé mode resonance is indeed affected by squeeze film damping. So this particular performance and the matrices gives us a record high figure of merit, that is the FQ product that we discussed in the previous slide. We have an extremely good FQ product, and this enhancement is being achieved merely through the structural engineering. We do not add to the power budget of this particular design. And once this particular support transducer technology was being demonstrated, it meant that we are no more restricted by the charge generation or the collection on the high Q bulk mode. That is, use another alternate mode operating at the same resonant frequency. This is an important condition. whatever bulk mode you're interested in, and whatever is the transducer mode that you want to use to excite this bulk mode, both of them should have the same resonant frequency, and they should be coupled such that they are in the high velocity region. So that is the two major requirements for support transducer topology to be successfully implemented. So multiple aspects were verified using support transducer. So we have not only used transducers which are oriented along the singular axis of silicon, we have tried combining 110 and 100 transducers. And not only were the fundamental mode explores, we tried to upscale the frequency to higher frequencies to see, okay, can we get higher Q or not? But it is very interesting to see that we still get quality factors of 25,000 and 18,000, even with a suboptimal or a poor transducer design, which means that there is a lot of area to be uncovered, a lot of research that can be done such that we combine the optimal transducer design and the high Q resonant feature. Now, this is a way that we tried. We did not change the transducer design. We simply scaled up the frequency of operation. And as you can see that we are able to get quality factors close to 30,000 in the ranges of 60 megahertz. And here in this particular design, we have attained 18,000. And another way that we looked is that can we explore the existing fundamental mode and their higher order modes. So not exactly the higher order radial mode, but a higher order mode in the radial structure. So this is a radial contour mode that you can see, as it's quite obvious that if you do a differential drive sense scheme, because of the similar polarity of strain across the four transducers, you will end up with no peak. And this is the common drive sense configuration and also the two-port measurements resonator design. This is one of a very interesting modes that we have uncovered. As you can see that even in air, the quality factor is about 18,600, and in vacuum, we get quality factor of 42,000. And this is one way that we can go to uncover these kind of unique modes which are unexplored in any MEMS domain to realize high Q resonators, which can be potential candidates for applications such as low phase noise or phase noise oscillators, channel select bandwidth filters, etc. And we did not only restrict to similar kind of resonators modes, we tried to combine multiple kinds of bulk modes. So please note that this is a very generic, simple design. It has not been optimized. So this is just to show that this is a proof of concept, rather to show that multiple different bulk modes, which has the same resonant frequency, can be actuated and sensed using the support transducer topology scheme. We have also investigated the possibility of using weakly coupled modes for applications such as mass sensors. We are also on the path to explore transducers along unconventional silicon axis such that they can be used to excite the gyroscope mode. So this is also a primary result showing that it is indeed possible to excite this mode, and still we need a lot of performance optimizations that will be carried out in the future stage. The next part of the tutorial will be focusing on the applications of piezoelectric MEMS. Since I have already covered multiple applications in the introduction to MEMS and piezoelectricity and also familiarization with piezoelectric materials, we will not be discussing much into applications, but I'll briefly go over the mostly used, the mostly explored domains where piezo MEMS are used. For example, filters, oscillators, mass sensors, inertial measurement units, IR sensors, or even in the audio regime. So let us start with the application overview.